stuff, share the real world stories, pictures, even videos that you guys might have seen that I showed you. That's the stuff you're going to walk away with and really remember. All these slides and stuff, you're going to have it for reference, whether you save your hard drives, maybe to help you down the road, years from now or whatever. But this for sure is what I wanted today's class to be most focused on. So we can either power on through or what do you guys feel like? But once I go through the PowerPoints, you guys are free to go because you'll have everything you need to get your 10 out of 10 on this week's quiz, etc. Cool. All right. So I'll go through these pretty quick, and the good thing is it's going to cover some of the topics that we mentioned either in passing or you already got eyes on in the instruction manual, right? I'm going to talk about cable connectors, like the crimping that you saw. We didn't have the crimp, the actual hydraulic crimp today, but in future classes, we're going to hold on to the specimens we've been working on. We're actually going to complete the crimps. And the last test, obviously, is, mechanically, you're following the instructions, you're doing your best to kind of make it physically good. But what's the ultimate test at the end of the day to see if this thing will stand up to being energized? Yeah, actually putting a megger on it, actually putting a DLRO if we land it. So that's going to come later on. So this was a really good initial crash course because you guys have become more intimately familiar with, now you can clearly see how normally all we saw is this, right? We see the ground braid, we see the stranded copper, but now we're really seeing how those bond to the cage shield, which we know runs hundreds and hundreds of feet in some cases. So now we know why this is a viable connection to test our insulation, right? We're really seeing that. And so I'm going to go over some more of these components and yeah, finish up from there. All right, so proper selection and installation of flexible cable connectors. Also see NEC articles for that kind of thing. All of you, well, most of you got to get in hand that lug, which you saw we measured out and fits right on here. So what makes a proper crimped lug connection, right? You saw in the, you had a picture of a report for the ones that were poorly done, where it looked like the improper crimp was performed on the lug. What kind of problems does that create? How do we avoid them? So what's the proper way to perform those, right? So on each of the lugs, I'm not sure if you saw close enough on the one you had, which again, real world stuff, he needs it for tomorrow, so make sure to take it with him. That's going to be installed in the facility. You're going to see some important information for us. Anybody able to discern what exactly that zoomed in portion is saying? 3 out, right? So that's 3 out lug. The top is probably the manufacturer. But yeah, it's focusing on the 3 out there for sure. What are we seeing on this side here?
The 50 for like 50 amp, I imagine?
50, so not in this case 50 amp, but it's more of a code. And we're going to see how that aligns with the Burndy crimp set. And also the color. The color is going to be important for us. What color does that look like?
Red.
Possibly. Could be. All right. Crimp terminations. The overall purpose is to ensure reliable electrical performance and excellent pull-out resistance. So we saw from the very outset of this class, the first thing, shock factors, we play that cable whip video, right? When we talk about how, don't just consider the electrical, also consider the mechanical performance or what would happen to your cables, right? If you have a poorly performed crimp, it will actually separate from the conductor, right? And yeah, Juan was alluding to how we have a pretty famous report, saved the customer millions, trillions of dollars, gazillions of dollars. So I'm like a hero there. No, that's not true. But we found a conductor was landed to a transformer that was generating a lot of heat, and this thing was messing up all the stuff around it, and was definitely going to cause catastrophic failure of the equipment. And when we investigated, we took it offline, we inspected the connection, and the lug was just sitting on the conductor, and then it was heat shrink on top. So they skipped the step where you actually crimp it and then heat shrink it. So the only thing holding the lug to the copper was the heat shrink, and so that thing was just a ticking time bomb, right? And so another valuable example of your IR camera being able to potentially save you millions of dollars down the road or however it may be, right? And so obviously the heat shrink itself is not the suitable application to for pull-out resistance, right? In this case here, a couple of styles: indent style, hex style, or hex flex die system. We're going to bring in a hydraulic crimp in a future class again to create the final product, right? And then we're going to put it to the test electrically, right? It may look good. I'm sure they're going to look fantastic when you guys all do your terminations, but the ultimate test is going to be your electrical test that we've become very, very familiar with in this class. All right. So when preparing the cable, strip the insulation to a length that allows the conductor to be fully inserted into the connector barrel with no bare wire exposed. And you'll see the Sharpie marks for those of you who couldn't see close enough. You can literally, side by side with the barrel of the lug, line it up, and then make your cut on the insulation, right? So you obviously don't want to expose too much of the conductor from here, right? Because that's where the funky stuff's going to happen. And obviously you don't want it too short on the other end either, because if the conductor doesn't reach all the way to the end, then you're missing vital points to crimp onto, right? To have that available surface area, to have enough crimps to, again, for excellent pull-out resistance. That's one of our key notes today, right? So, and we did just that, so we were able to see that very close up. When choosing the proper connector, you'll note the following indications, and we saw this on the previous one, maybe that red-orange color code we saw, the 50, right, the die code 50, and we saw the 3/0, so we know that that lug is specified only for a 3/0 cable. Right, so you're going to see things like manufacturer application by color die code, bar size, crimp indicator bands, UL listings. Crimp indicator bands are simply going to be these guys here. Going to be our black color code, for example. Looks like 106 is your die code, and you're going to have strips, these color stripes that will actually tell you where to perform the crimps. And this has become going to be more apparent when we're looking at our die sets, so we'll know exactly how they line up. And you guys will be able to actually perform your crimps. We're going to talk about how to do them properly, and then we're going to actually perform them and put them to the test, right? Electrical and mechanical wise. Also note copper or aluminum. Your lugs are actually going to say what it's suited for, right? Right tool for the job. So copper and aluminum, we've talked about electrical performance, for example. We've talked about melting point, flash point, that kind of thing. But obviously we know that they have different ductile strengths. So that's going to dictate, do you have the right lug for this particular material? Choosing the proper tool and die. Connectors with colored bands or dots that correspond to the colored markings on the dies facilitate proper matching of connectors with dies. So when it comes down to that red-orange we saw, well then your die set is actually going to have that matching color, right? Informative Annex Q of NFPA 7E, humans make mistakes. So let's make it easy to do the right thing, hard to do the wrong thing. When the colors match and the die codes match, those 50s match and the 106 all match, then we know we're doing the right thing, right? We want to set ourselves up for success, and we've seen how complicated these processes can be, how many specific steps it takes. So definitely alley-oop ourselves to make sure we're doing the right thing, doing it properly. Connectors and dies also have a die code. We talked about that one, for example, the 50 and the 106. Dies have a code number engraved on the crimping surface, so definitely lots of indications to make sure we're doing the right thing. And yet somehow in the report from the plugs that blew up, they used the wrong crimp somehow. So if somebody could screw it up, well, that's good for my company. So here's an example of the dies and connector markings. We're going to bring in the whole die set with a hydraulic crimper, battery powered, so good for, it's pretty big and bulky still, but definitely more mobile than the stuff they used back in the day where you try to have your hydraulic set, right? In this case, this is battery operated. So yeah, we'll bring in a good one for you to be able to use. We're seeing all kinds of color codes, white, yellow, ruby, blue, red, etc., to make it easy to do the right thing or do the wrong thing, hopefully. So when it comes to proper crimping, first you'll locate the markings on the connector and die. For example, we were looking at these bands. Keep those in mind, black band there. And so obviously you're going to use your, it's a gray, maybe black is one of our other guys here. Tough to see. But you're going to match up the markings where it actually performed the crimp to the indicator bands. Insert the connector into the tool and align the die with the connector. You're going to see there's a couple nuances to that one, but once you get hands-on, we'll really dive into the weeds on that one. With multiple crimps, the first should be nearest to the tongue, and subsequent crimps should be toward the barrel end. So this one I'm going to let sink in a little bit for you because this is very, very important. One kind of touched on this a little bit, but visually we're going to take a deeper dive. The last slide stated that you're going to start on which end? Looking here, left or right, according to it. Left side, right nearest to the tongue. It's kind of an intuitive way to look at it. So this is kind of the tongue portion. Where kind of looks like a tongue. So you're going to start on this end, performing at the various indicator bands, right? And you're going to move towards the outside. right? That's the proper way to crimp. Does anybody have any guesses as to why that is the proper way to go? Any guesses? Wild guesses?
Left to right?
Yeah, yeah. Or as opposed to the other way, and what could be some complications? Yeah, Jason.
Maybe because when you start from the front, it'll like pull it in. But once you continue the other crimp.
Yeah, so you could have alignment issues. You could have some funky stuff going on. Jazz, what do you got?
Same thing. I mean, now, we're talking about like the crimper as far as like being able for the teeth to like actually grab the whole thing.
Yeah, yeah.
So, yeah, I mean, if you start it from the right, then you're not gonna get the full way from the left.
Yeah, and so for example, when crimping from right to left, you're actually going to expand this guy here. You know the choke point is going to be on the tongue, right, where it meets. But as you're crimping this way, you're actually kind of spreading it outward, so you're going to get worse contact towards the tongue, right? Whereas from here, if you start from here, even if it fans out, it has that give to be able to still, you know, maintain, and you'll always be able to perform the correct crimps. Whereas starting from the other end, it's you know, you're more prone to you know, messing up the connection there. You know, poor surface area, poor contact. And what happens when you make poor contact between energized conductors?
Causes heat.
Causes heat, definitely your heat buildup. And how do we test for that electrically?
Amperage.
Yeah, ampere, yeah, the DLRO, because we push amps through here. We check the resistance. We know high resistance is high heat. So your DLRO, your ductor connection, will actually test that maybe you have a poor crimp connection, right? And we know, again, that's the big three of electrical connections, right? Your IR will expose, you know, poor crimp, just like the example I told you. Your DLRO will tell you you have a poor connection from your conductor to lug. And the last is your calibrated torque wrench, and that's specifically for this portion of the connection. So we're not worried about that one for now, right? So remember, and that'll be a quiz question. There's a little hint for you. Which end are you starting the crimp from? So again, it'll be nearest to the tongue, out towards the barrel end, because it'll allow for any kind of expansion of the metal.
Can you draw?
Connectors are marked with.
Can you draw that? What you just said, nearest to the tongue,
Yeah,
to the barrel end?
so here, so kind of the tongue, you get how they might call this the tongue, the tongue sticking out that way. So you're gonna start from this end and then work your way out towards the barrel end. So just think tongue end and barrel end, like a barrel.
That's where you want to slide it over?
No, we're talking about crimp. So
Oh,
crimp
crimp.
here, crimp.
Oh, I see, gotcha, yeah.
So 3, 4, however many the indicator bands dictate.
Mm-hmm.
Just because you know that it'll expand, kind of fan out.
Mhm.
So you want to make sure that you're going out towards the barrel end where it'll actually accommodate that.
Isn't that prone to slipping though?
Well, that's up to you as the
How hard do you-
technician to make sure that you've got a firm grip on the components. And well, you'll see when you get the hands-on portion of the actual crimping tool, we'll talk about the ways you can back off. If you know you have a misalignment or a bite, you can actually, there's a valve where you can, because it's hydraulic, right? You'll actually let the air escape to be able to reset your crimp. So we'll get plenty of practice with that. We're going to crimp a number of connections, and there are going to be plenty of indicator bands, so plenty of chances for you guys to get hands-on if you want to take advantage of our hands-on opportunities in this class. So the last part, your connectors are marked with colored stripes to indicate the number and location of each crimp and the die code number in each compression location. This is more visible with the orange, right? Where we can see you can actually get onto the thick band, for example, if that's what lines up with your die, your actual die set. Right? And so, again, this is just your crash course, informational, and enough to do well in your quizzes. But when we bring the die set out here, you'll be able to put this all to use and become very familiar with the equipment. Cool. So that's first set here. Next set of slides, and again, yeah, it's actually really beneficial that having Juan come in with the hands-on. Now we have something directly to relate what we're seeing, at least informationally, to something that we've already become familiar with one way or another. Medium voltage cable insulation ratings. Again, there's a handy reference to the NEC. Okay. So far, reading some of our cable nameplate information. On seconds, it might say something like, and in this case, 5 kV, 133%, 8 kV, 100%. I'm going to pass this around. So, yeah, feel free to give that a read. And so, if you've seen that on our cables before, you're probably wondering, well, which one is it? 5 kV or 8 kV, right? And so now we're going to pull back the curtain on what each of them means and what these percentages you're seeing. I'll go ahead and read out what that says for this specific example. And I think,
5 kV, 133%.
yeah, this is not the other. Go ahead and check that one out as well. So which one is it? Right?
8 kV is
Shot, or
100%.
what's the deal? Right.
Oh, because there's a dash between 133% and 8 kV.
And so you can tell that depending on, so this is going to come down to the application. What is this cable going to be used for? What's it going to be installed, for the purposes, right? And so we're going to talk about what those numbers mean exactly. So the three different installation categories you're going to see: 100%, 133%, like in these examples here, and you may even see 173%. So these are the three you're going to see. These all pertain to the thickness of the insulation, So for 100% rated cables, they may be used on a system where ground faults are cleared as rapidly as possible via a relay protection scheme. The key for this one is going to be that faults are expected to clear in less than 1 minute. That's going to be your 100% rating. So this, for example, the system is probably solidly grounded, low resistance grounded, or lone beam grounded. And so, at least for the purposes of your quizzes, we're going to sort them by your cable rating as well as the expected clearing time, right? So we talked about how the application is going to dictate, which you're going to use, the 5 kV at 133 or the 8 kV at 100, right? So if nothing else, pay attention to the bold portion so you can get your 10 out of 10 in school. So 133% may be used on systems where ground faults are to be cleared within an hour, right? So 133% for an hour. It could be high resistance grounded systems. Those of you in the transformer class might know about our HRGs, which we talked about a little bit. And then finally, our 173% rated cables permitted in facilities where the conditions of maintenance and supervision ensure that only qualified persons service the installation, and the clearing time for the ground fault may exceed 1 hour. So in this case, 173% may exceed 1 hour, and obviously extra layers of complication where an orderly shutdown is essential for protection of personal property, and there's adequate assurance that the faulted section will be de-energized in an orderly shutdown. Right, so at least correlating the percentage. Yep.
What kind of normal equipment would have a ground fault for an hour?
the kind,
I'm not familiar with it. So
Yeah,
it sounds
yeah.
crazy.
yeah,
You know,
I'll
like,
see if I can
we'll
get you
try
a
to go for
concrete
an hour.
example. But for some of the, I guess, more forgiving, robust type installations, I'll see if I can get you a solid example, but they definitely exist. For example, upstream where they use like recloser, kind of recloser setups.
The only thing I could think of was like a utility.
Yeah, line sectionizers,
Something
line
like that, maybe,
sectionalizers in combination with reclosers.
Yeah.
Where
Like
you
a
probably
tree
see them
that they
use.
it takes
Yeah.
an hour just to get to it.
Yeah.
Like
yeah,
something
that's a good
like
example.
that's the only.
But definitely upstream for higher voltages kind of thing, and that's why you could tell it's definitely correlated with the higher consequence or even a higher risk involved. And so here, so we talked about how it's insulation thickness, right? And so we're going to see this translated to the actual physical properties of it, whether in millimeter or mils, right? I'll let you look at this real quick. Before example, we saw our example was 5 kV at what percent?
130.
Cool. And then the other corresponding one, so here's our 5 at 133. We have 2.92 and 115. And what was the other value for those cables?
100.
Yeah, 8 kV, 100. 100, yep. And what are we seeing here? 2.92, 1.15. So here we're seeing why that exact correlation exists, because the thickness is one and the same. And again, is it being used for a 5 kV system or is it being used for an 8 kV system? If it's used for a 5 kV system, then you can clear your fault in less than an hour. But if you're using it in an 8 kV system, it is then only specified clear in less than a minute. And so you're seeing that exact kind of shared property here. And so here's some more examples. 15 kV cable, which will actually possibly be one of our subjects for cable terminations on the 3M kits, right? So you can see some examples of what we're going to be seeing here in insulation thickness, right? If you look on, for the cables still floating around, anybody able to find me this number? Because that should be written on there. Who's got it here? Ismail, are you able to see 115 on there? And then, it's luck of the draw because you know, obviously doesn't show a full length of cable. And so maybe, okay, here, I'll bring this back to you. You'll see that right there. Go ahead and pass that one around. That one says 115 mils. So you can tell that that corresponds exactly with the 5 kb 133% and 8 kb 100%. So 115 mils of actual physical thickness. All right, and so these will be your handy references again, if nothing else, for the purposes of doing really well on the quiz. Cool. That's the end of that slide. And the last set we're going to do for you is the minimum bend radius, which is actually this is more of a handout. So this is going to be an informational handout. Give this one a read for more details on it. But there is a table in your NETA MTS book. If you have that, if you have your books out, go ahead and give your book a flip to the back. I'm going to pull up my copy as well. And see if you can locate the table that speaks to acceptable bend radius. And so the general idea with this is, so they talk about allowable bend radius. Allowable bend radius, what do you guys think that is pertaining to? Right, and for those of you who've, ventured into the journeyman exam, you talk about, how many 90s are permitted, etc. It might be along those lines.
Basically, if you bend the cable too much, like if you
Yeah. So what would be bad about bend?
It could crack the insulation, or
Yes, exactly.
break strands inside, or like something would break and it wouldn't work right.
Yeah, and so separation of strands, separation of the strands from the semicon, which we've become very, very familiar with, that black layer of the semiconductor material that fills in the gaps of the stranded copper, for example. So once you separate these layers, what do you risk?
Oh, the air contaminants getting in there.
Yeah, and air gaps. What happens within those air gaps?
Start breaking the insulation.
Yeah, and so you're talking about heat can be generated in there, right? And then heat's going to cause melting of those components, which is only going to create more heat, which is going to be more funky stuff, which is going to create more heat. So yeah, this is going to take off. They call that thermal runaway, right? And eventually, boom, and then they call that company. So this is going to be a useful table for you, 100.22, if you haven't already found it in your books, right? And so you're going to see it sorted by cable type, right, as well as your overall diameter of the cable, and that's going to speak to the minimum bending radius as a multiple of cable diameter. So this might get pretty confusing. Lean on your handout for more information, but note that this is not, the value, in inches or whatever of the radius, but is the minimum bending radius as a multiple of the cable diameter. So pay attention if they're asking for the actual value, maybe 2 inches, for example, or they're asking for the multiple of the cable diameter. So just a heads up on the quiz, it will be broken up into different parts asking, hey, what is the multiplier and what is the actual measurement, right? And then the final question is kind of setting you up for, okay, you take the multiple, you multiply it by the actual measurement, and then there's your final actual measurement. Right? So just bear with it, do read the instructions very, very carefully on your quizzes, and again, lean on that handout for extra guidance on this.
So if it's a 2-inch cable, it'd be twice that.
Bingo. So 2-inch cable with a 12 multiplier would be, what's your level? 24. Yeah, piece of cake, right? So the math is easy, but how you get there is going to be, if anything, the tricky part. But nothing's going to get past you guys, right? So identify the type of cable that's being asked about. All right, you're going to be given, with enough variables, you can always calculate for the last thing, right? So if you're given a 2-inch, it'll fall, in this column here. And then your multiplier might be 15, and then maybe it's 30. So that's just an example. And again, you have unlimited tries for all your quizzes and stuff, get the grade you want. So just pay attention, you're answering the correct quantity in the correct field. It's as easy as that.
Bending
Other than
radius?
that, as promised, it's pretty much powering through the dry stuff that we'll need for our quizzes. The most important was, the experience that you were able to walk away with. Hopefully you took advantage of the hands-on opportunity here. This is real-world stuff. I'm going to keep these gloves for future instances. and other equipment. Other than that, yeah, you guys are free to go. You have everything you need. But as always, I'll stick around for makeup labs, or if anybody wants to keep messing with these terminations, or anybody wants to explore band radius further in detail, that's exactly what I'm here for.
This is-
We're right on time, like we said, after the midterm, 9 o'clock and onwards, we want to do open labs, so good to go.
Bending radius chart?
Yeah. In fact, yeah, let's talk about that now. Once anybody who wants to make their great escape do that. So, you got your values?
Yeah.
Cool. Did you write them down? Oh, you took pictures? No. Yeah. Go ahead, put up on the board. Solve for me the DAR and solve for me.
Oh, I just did the PI.
Well, did you get the numbers for the DAR? What does the DAR consist of? Like which two values do you need? It's in the slide. Not quite. There are two time-based quantities. So, for example, this is your
Resistance and resistance interval.
10 minute or your 1 minute. This is another time-based test. Check your slides for which
I think so.
From last week or previous?
it's in the previous slide. Yeah, but then it'll give you a formula kind of similar to this, but because you have the numbers to back it up, you can tell me what your particular.
Oh, isn't it 1 minute? You got it, man? I would assume because you only do one word. That's good. I know it's 1 minute.
It's 1 minute over something.
I did a different one.
Feel free to reference your notes. Yeah.
At least I got the jacket off. That's good.
It's for the cable rating, they go based off of how much is gonna be running through.
Yeah, exactly. So if you got a 4160 motor, well, you know you can go for 5 kV.
Oh, so you're
at 130.
referring to voltage across phases, not voltage ground?
It would be for the nominal system range, like